In this lecture, we'll continue our discussion of the application of Newton's second law to various problems, various scenarios. And we'll start with the problem, this one right here, which involves a truck which is parked on a 7-degree slope. And the question that's being asked is how big is the force of friction, frictional force on the truck? So again, in all these problems, the first step is always to draw a free body diagram. So we're going to start off with the free body diagram of the truck and based on our discussion in previous lectures, whenever you have a situation where you have an incline, then it is best to choose your coordinate system kind of adapted to this incline. In other words, make sure that one of your coordinate axes is parallel to the incline. So in this case, we'll do the same. We'll choose our x-axis along the incline. And of course, the y-axis has to be perpendicular, so it's going to be perpendicular to the incline. So that's your x-axis, your y-axis, and we're going to start off with the free body diagram. What are the forces acting? Well, we know there is the weight of the truck acting in the downward direction, and there is the normal force. Now, remember, the truck is parked on the incline. It is not sliding down. And if there were no friction between the tires of the truck and the incline, this truck would in fact be sliding down. It doesn't do so. So the force of static friction is what prevents it from sliding down. So we've got a third force, which is the force of static friction acting in this direction. So you got the weight, you got the force of static friction, and the normal force. These are the three forces acting on the truck. Now, we've got to figure out, notice the weight acts at an angle is not along the x-axis or the y-axis, so you got to specify the angle that it makes with one of these axes. And the easiest way to work this out is they give you the angle of the incline, which it's a 7-degree slope, which means this angle right here is, let's call that angle theta, which is 7 degrees. Coming back here, if this angle is given to be 7 degrees, notice the weight goes straight down. Again, thinking in terms of right triangles, this angle is a 90-degree angle, which means this angle right here has to be 83 degrees. Okay, if this angle is 83 degrees, you could work with this angle. I personally prefer working with the same angle that's given here, which means this angle here is the same as the angle of the incline. Okay, so the angle that the weight makes with the negative y-axis is the same as the angle of the incline. Now, once we've got that, we can go ahead and work out the x and y components of resolve the forces into components, something that we have done in previous problems. So we're going to list the force in one column, x component and the y component. List the forces. You got the weight, the force of static friction, and the normal force. In this case, let's make this very clear. This is just the force of static friction. It's not the maximum force of static friction. We know that there's just enough friction to prevent this from sliding. It's not necessarily the maximum force of static friction. So we just leave it as just the force of static friction. Now go ahead and resolve these into components. So weight has an x component, and as you can see from this sketch, it is minus mg sine theta. This is negative mg cosine theta. The force of static friction is in the positive x direction, so along the positive x-axis, so that's plus f sub s, 0. And the normal force is in the along the positive y-axis, so that's what we have. Now, to answer this question, how big is the frictional force? Well, we've got the net force in the x direction is f sub s minus mg sine theta. And we also have another equation. The net force in the y direction is n minus mg cosine theta. Applying Newton's second law. Newton's second law says just the net force in the x direction, is mass times the acceleration in the x direction. Net force in the y direction is the mass times the acceleration in the y direction. We know right away, since the truck is on an incline, it's not leaving the incline. This for sure is zero, even if the truck were to slide down the incline. So that the y component of the acceleration is definitely zero. In this case, since the truck is at rest, the x component is also zero. Why? Because the truck is at rest. Now we can combine these equations with this one together. We end up with the equation. In fact, let's look at the y. So if you want to answer this question right here that's being asked in this problem, since they're asking us for the normal, or whoops, I'll take that back. Let me not do it. So looking at the x component of the net force, we have f sub s minus mg sine theta is equal to 0. So let me just mark these out just to show you how I'm getting that equation. So it's this equation along with that equation. I'm just combining them to give you this. That gives you this equation right here. And from here you can solve for the force of static friction, which is just mg sine theta. The mass of the truck is given to you. It's a 4,000 kilogram truck. You know the angle theta, and so you can figure out the force of static friction, that many newtons. What is the other equation good for? So, well, from the second set of equations, and I'm just going to draw it that way, and this equation right here. I'm sorry, this picture is getting a little complicated, I know. So if you look at the y component of the net force, well, that tells you that n minus mg cosine theta is equal to 0. And from here, you can get the normal force, which is mg cosine theta. So you can get that. Of course, this particular problem is just asking you for the force of static friction, but the other equation would also will allow you to figure out the normal force acting on the truck. Okay, here is another problem involving an incline. You got Jason works for a moving company. A 45 kilogram wood crate is sitting on the wooden ramp of his truck. The ramp is angled at 11 degrees. What is the magnitude of the force directed parallel to the ramp that he needs to exert on the crate to get it to start moving? So you got a ramp which is inclined at an angle of 11 degrees. So that's theta, which is 11 degrees. The first part of the problem says, what is the force that Jason needs to exert so that the crate just starts moving up the ramp? Okay, so that's the scenario that we're looking at. Here again, we're talking about an incline, and so we choose our, so we're going to draw a free body diagram. Let's start off the free body diagram of the crate. And the free body diagram of the crate is going to be, well, the first step, we're going to choose our x-axis along the incline, y-axis perpendicular to the incline, and oops. Okay, there we go. The forces acting on the crate are the weight of the crate in the downward direction. Let's keep this. there is the normal force acting perpendicular to the ramp. There is Jason is pushing it up the incline, so there is the force that Jason exerts. And finally, there is friction, and the whole idea is for Jason to exert enough force to overcome the force of static friction. So the force acting on the crate when Jason just gets it moving is the maximum force of static friction. So that's the force of friction that we're talking about here. Let me just go ahead and label these forces now. That's the weight. And just to remind ourselves, that's the weight. There is the force, let's call that the applied force. And that this is the normal force. The notation speaks for itself. So, well, since we're doing it, let me let's remind ourselves what these are. So the maximum force of static friction. And like I said, I always like to write which body is responsible for each of these. That's the Earth. That's Jason. That the normal force is, of course, the ramp. And this force of static friction is also exerted by the ramp. Okay, so that's the sketch that we have. And again, we need some angle out here. This angle, the angle that the weight makes with any of the axes. Again, just as in the previous problem, since the angle of the ramp is given, the angle at which the ramp is inclined is given, that angle is the same as the angle the weight makes with the negative y-axis. So these two angles are the same. A little bit of properties of right triangles. Okay, so we've got this. Now here again, let me emphasize, why do we choose our axes in this awkward manner? Because it simplifies the problem. And here it is very clear. You've got four forces acting on the crate. Okay, of these four forces, three of them are along either the x or the y axis, and only one of them has both an x and a y component. Now this was achieved because we chose our axis in this particular manner. If we had drawn our axis the usual way, this way, you will see it's only the weight which will be along the negative y direction, but every other force is going to have both an x component and a y component. It would be a really messy problem, okay? So that's the advantage of choosing our axis this way. Now we go ahead, and if you resolve the forces into components, again, you got to get really comfortable doing that. And I'm just going to write them down very quickly. So the forces are going to be listed in the first column. Force, x component, y component, the weight, the applied force that Jason exerts, the normal force, and the maximum force of static friction. The weight is going to be minus mg sine theta, pointing in the negative y along the negative y-axis, and this is minus mg cosine theta. Applied forces in the positive x direction. Again, I never did label the axes. That's the x-axis, that's the y-axis. So that's going to be plus f and 0. That's 0 and plus n. And the maximum force of static friction is in the negative along the negative x-axis. And we know that that is just the coefficient of static friction times the normal force, and that's going to be 0. Okay, so we'll build up this table. Now we're talking about wood crate, which is sitting on a wood ramp. So here I've listed, so for looking back at the table of the coefficient of static friction, we know mu sub s for wood on wood is 0.5. So we have that fact as well. And we also know the mass of the crate. That's the mass of the crate given to us. Let me list that here. Mass of the crate is a 45 kilogram crate. And of course, we've already used this fact that the angle of the ramp is 11 degrees. Okay. Now the net force in the x direction is the sum of all the forces in the x component of all the forces. So you have F minus mg sine theta minus mu sub s times the normal force. And remember, the crate is just about to move, so we are going to minus, what did I get? Yes, is equal to, well, let's leave it at that for now. We'll come back to that later. Net force in the y direction is n minus mg cosine theta. And we are doing the first part. Let's say, what are we interested in this part? So in the first part, we want to determine F. So the crate starts moving up the incline or up the ramp. Okay, it's because it's just about ready to start moving up the ramp that gives us the direction of the force of static friction. It has to be down the incline. Now, applying Newton's second law, we know that since the crate is at rest, crate is still at rest. It's just about ready to move. You've at rest. We know the accelerations in the x and y direction are 0. And so Newton's second law. So from Newton's second law, we know the Newton's second law says that the net force in the x direction is 0. Net force in the y direction is also 0 because the accelerations are 0. And now we have the equations. We have F minus mg sine theta minus mu sub s times the normal force is equal to 0, and n minus mg cosine theta is also equal to 0. You got two equations. We are interested in the force, magnitude of the force F, and so that's the unknown that we're talking about. F is the unknown. But if you look at this equation, you know the mass, you know the angle theta, you know mu sub s. Like I said, it's 0.5, but we don't know the normal force. So the normal force is also an unknown. So you got two equations, two unknowns, so you can obtain them both. Well, since we are interested in the applied force, what we're going to do is we're going to work with this. The equation 2 tells us that n equals mg cosine theta. Once we have an expression for n, we are going to plug that in back into the first equation, and from there we get F minus mg sine theta minus mu sub s mg cosine theta equals 0. Oh, sorry. Fe. Yes, I was correct there. That is correct. Equals 0. Or F is equal to mg sine theta plus mu sub s mg cosine theta. Again, now you got everything here is known, and you can figure out the applied force, the force that Jason needs to exert to get the crate moving up the incline. Part B of this problem is to determine the force required. So now the setup is, so what we have is we still got that crate on the incline, and put that there. There's our crate. And the question is, what is the force that Jason needs to exert so that the crate starts sliding down the incline? So determine F so that crate starts moving down the incline. So the approach is pretty much the same as before. We're going to choose we're going to draw the free body diagram. And in order to do that, we're going to choose our axis in this particular manner, x-axis, y-axis. This is, of course, we are sketching the free body diagram of the crate. Forces acting on the crate are the force of gravity, the pushing force directed this way, normal force is acting that way. Now the force, you're trying to get it to slide down, so friction prevents it, and Jason exerting the force required to overcome that frictional force. So the force of friction is going to be the maximum force of static friction, in this case acting in the upward direction along the incline and upward. So here we go. There is the weight. There's the weight, the maximum force of static friction, the normal force, and the pushing force. You can go ahead and, so we're gonna resolve the forces into components. Force, the x component, the y component. The only big difference is, as you can see, this angle is also theta, just as before. Most of it is the same as before. Our discussion hasn't changed. So you got these forces. And like I was saying, the weight is going to be minus mg sine theta minus mg negative mg cosine theta is going to be plus mu sub s. That's the big difference. In the previous part, it was in the downward direction. The maximum force of static friction was along the negative x-axis. Now it's along the positive x-axis. And that is the big difference here. Everything else stays and the pushing force, of course, is also in the negative, along the negative x direction. And you've got mu sub s is given to us. Mu sub s is 0.5 as before. And now you can go ahead, and I'm going to leave it at this. You can go ahead and similar approach as part A to find F. Okay, do the same thing as you did before to figure out the F. That is, you write the net force in the the x component of the net force, the y component of the net force. Again, the accelerations are 0. Write them out, and you can figure it out. Okay. Continuing with these inclined plane problems, where objects are on inclines. Here's another problem where you have a child. A 23 kilogram child goes down a straight slide inclined at a 38 degree inclined 38 degrees above the horizontal. The child is acted on by his weight, the normal force, the kinetic friction, and the horizontal rope exerting a 30 Newton force. Okay, so let's look at the child here. So in this child, the child is going down the incline, there is friction. But in addition to all the forces acting on the child, there is this additional force exerted by a rope on the child, pulling the child in the horizontal direction. Okay, so again, without going through too much of the details, let me just set up the problem for you. But here, the problem only asks you to figure out the normal force. But there is a lot more you can do with this problem. So let me go ahead and set it up that way. So you've got, there is the free body diagram of the child. What are the forces acting on the child? There's the weight, normal force. Child is sliding down. We're talking about a child who is sliding down. So the force that the frictional force that we're talking about is the force of kinetic friction. And now you also have the tension in, there is a rope. Is that a rope exerting a 30 Newton force? Whenever we talk about ropes, we talk about the tension. So there is an additional force there. So again, that's the weight. There's the weight, the tension exerted by the rope, the normal force, and the force of kinetic friction. The child is sliding down. This angle here is the angle theta of 38 degrees. So theta is 38 degrees. The tension has a magnitude of 30 newtons. The mass of the child is 23 kilograms. 23 kilograms. So okay, keep that there. So if this angle is theta, like we have done before, the same as this angle is theta. Now in this case, there is the tension that makes an angle with the is not along the x or the y axis. So we got to figure that angle as well. So if that angle is theta, that angle is 90 minus theta. So again, looking at the sketch here, you can argue that the angle that the tension makes with the x-axis is also theta. Okay. And now you go ahead and resolve the forces into components. And so we're going to list those. Here, there is the force, the x component, and the y component. The forces are the weight, the tension, normal force, and the force of kinetic friction. Tension, like before, as the x component is, in this case, plus mg sine theta, because if you work this out, that is the x component. Don't forget, make sure you're picking the right sign so that it points in the along the positive x-axis. So it's plus mg sine theta. Y component is negative mg cosine theta. That's the y component, negative mg cosine theta. Tension, x component of the tension is plus t cosine theta. Y component is plus t sine theta. Normal force is along the positive x-axis. Frictional force along the negative x-axis. Did I say normal? Normal force is along the positive y-axis. Frictional force along the negative x-axis. And we know the frictional force is negative mu sub k times the normal force. So that's what we got. Now we've got the net force in the x direction is t cosine theta plus mg sine theta minus mu sub k times n. Net force in the y direction is n plus t sine theta minus mg cosine theta. Newton's second law. Newton's second law says that the net force in the x direction is mass times the acceleration. x component of the acceleration. Now in this problem, the child is sliding down the incline, okay? So in some sense, the child could have an acceleration in the an x component of the acceleration, and in fact that is an unknown in this problem, okay? As it turns out, for the question that's being asked, we don't have to worry about that equation, or we don't have to worry about that, but that's an additional part that you can add to this problem. We'll get to that later. So at this point we say, we don't know what that acceleration is. And there is another equation, the net force, the y component of the net force, which is n plus t sine theta minus m, I've jumped a step there, is in fact mass times the acceleration, sorry about that, y component of the acceleration. Here we definitely know that the acceleration, y component of the acceleration is definitely 0, because the child, no matter what the child is doing, what the acceleration is down the incline, we know the child is not leaving the incline, so the y component of the acceleration is definitely 0, okay? So if you focus on the net y component of the net force, we have the equation n plus t sine theta minus mg cosine theta is equal to 0. And from here, as far as this problem is concerned, n is just mg cosine theta minus t sine theta. And you can go ahead and work this out. Always do that, but I've got the answer with me. But again, never trust my answer. Just go ahead and definitely verify that this is in fact the correct answer. So put a question mark out there. But as far as this question is concerned, that's all that's being asked. What is the normal force? It's mg cosine theta minus t sine theta. But I can add an additional part to this problem. So call that an additional part. And the additional part is, say, if the coefficient of kinetic friction between the child and the slide is, say, 0.2. So this is the coefficient. So if this was given to you, of kinetic friction between the child and the slide, then what is, let's say, what is the acceleration of the child down the incline? Okay, so that is an additional part that could be added. Well, now we just have to focus on, so we focus on the x component of the net force, and we know that the x component of the net force is equal to mass times the x component of the acceleration. And we have the following equation now. We've got t cosine theta, or I'm going to write, since we're trying to figure out the acceleration, I'm going to write it as m mass times the x component of the acceleration is t cosine theta plus mg sine theta minus mu sub k times n, or the acceleration would be t cosine theta plus mg sine theta minus mu sub k times the normal force over the mass of the child. And you could figure out that acceleration. The tension is given to us. It's 30 newtons. You know the coefficient of kinetic friction. I just gave it to you. As far as the normal force is concerned, well, we've just solved for the normal force. So we have the normal force here, and the value that you get for the normal force is what's going to go there. Everything else is given. All these are known quantities, so you can actually figure out the acceleration. Again, just continuing to look at various scenarios, various types of problems where you can apply Newton's second law. Here, what you've got here is a 10-kilogram crate is placed on a horizontal conveyor belt. So that's your conveyor belt, and you've got a crate on the conveyor belt. The materials are such that mu sub s, the coefficient of static friction between the bottom of the crate and the conveyor belt is 0.5. Coefficient of kinetic friction is 0.3. And I'll let you handle the first two parts, that's drawing free body diagrams. And I'll start with part C. So I'm going to start off with part C of this problem. And in part C, what is the maximum acceleration the belt can have without the crate slipping? So in part C, the crate is not slipping. And has its maximum acceleration. Okay, so this conveyor belt is moving as fast as it can with the crate moving along with it without slipping. That's the without sliding or slipping on the conveyor belt. So again, as with all other problems, we start with a free body diagram of the crate. Now, one thing to note here is that if there were no friction between the crate and the conveyor belt, then if you start moving this, what's going to happen is the conveyor belt is just going to slip below. The crate will just stay where it is, and the conveyor belt is just going to be sliding underneath the crate. Okay, so there has to be static friction between the conveyor belt and the crate if the crate is going to be moving forward and if it's going to be accelerating forward. Okay, so well, what's the free body diagram going to look like? Here's you draw your x and y axis, and we go ahead and put down all the forces. There is the force of gravity, or the weight. We've got the normal force. And now what is driving the crate, accelerating the crate in the forward direction? Like I said, if there was no friction, then the crate would move from underneath that would be the direction in which the crate would be moving, and the conveyor belt would be moving and the crate would just stay there. So what's allowing the crate to move in the forward direction is in fact the force of static friction. And since the crate is moving at its maximum possible acceleration, this force, the force of static friction, has its maximum possible value, which means, well, let me just label all these forces first. That's the weight, normal force. This force is in fact the maximum force of static friction. Why maximum? That's because in the statement of the problem, we are told that it is not slipping and it has its maximum acceleration. So the fact that it has its maximum acceleration means the force of static friction is also taking its maximum value. Let's focus let's focus on the net force in the x direction is in fact Fs max. And we know that the maximum force of static friction is mu sub s times the normal force. Net force in the y direction is N minus mg, the normal force in the along the positive x-axis, weight in the negative along negative x-axis. And we know that it is not leaving the conveyor belt, so that's equal to 0, which means this equation says N equals m times g, as you would expect. And now you can go ahead and plug N back into this equation right here. And we also, well, let me write. So also the net force in the x component of the net force is mass times the x component of the acceleration. So combining all these facts, we have mu sub s times mg equals m times a sub x. How did I get this equation? Well, the x component of the net force is mu sub x times n, but n is mg, and that's how I get this expression for the x component of the net force is mass times the acceleration. That's just Newton's second law. Notice the mass of the crate is kind of irrelevant in this problem, and it's given to be 10 kilograms, but you don't really need it to answer this part. And we have the maximum acceleration is mu sub s times g, and this here is the maximum possible acceleration without slipping. Okay, and then we have part B of this problem. Now what's happening is you just crank up the speed of the conveyor belt, and at some point what's going to happen is, well, remember the force of static friction is maxed out, and if you just crank up the speed of increase the acceleration of the conveyor belt, well, now the crate is not going to stay with the belt, it's not going to move, it's not going to be it's not going to have the same acceleration as the conveyor belt, and now it's going to start slipping on the conveyor belt. Okay, even after it starts slipping, it's still going to be moving forward, but with some slipping happening as well. And the question that's being asked in part B is if the acceleration of the belt exceeds the value determined in the previous part, what is the acceleration of the crate? Okay, so the crate is, so here we go, just summarizing that. So the crate is slipping on the belt, and still accelerating forward. Okay, and here again, what we are supposed to determine is the x component of the acceleration. And as before, do the same thing, free body diagram. Well, let's just do thing. Make that a little bit more. There is the normal force. And of course, now what we have is, since it's slipping, since the conveyor belt, the belt is kind of sliding from underneath the crate, essentially what you have is what you're going to have here is the relative to the conveyor belt, the crate is kind of moving in that direction relative to the conveyor belt. And so what you have is the force of kinetic friction is opposing that motion, and so the force of kinetic friction is going to be in this direction right here. And so we have the force of kinetic friction is directed this way. Okay, again, try to visualize. If you were standing on the crate, what do you notice? You will see, if you're standing on the conveyor belt, you will notice that the crate is, I mean, of course, the conveyor belt is going really fast. It's got this large acceleration, but this one is kind of moving in exactly the opposite direction. And that's what tells us that the force of kinetic friction is in the positive direction. So we got the weight, the normal force, and the force of kinetic friction acting in that direction. So the bottom line, comparing it with the previous part of the problem, what we have now is the maximum force of kinetic friction, of static friction, is replaced by F sub k, which is the force of kinetic friction, and the direction is still the same. And I'm gonna let you handle the details left as an exercise to determine A sub x. Only thing to note here is that the force of kinetic friction is mu sub k times the normal force. And remember, in the statement of the problem, mu sub s and mu sub k are both given here. So you're going to replace in the first part, of course, mu sub s, the mu sub s that you have here is 0.5. And in the second part, when there is slipping, you've got mu sub k, which is 0.3. That's the only big difference, and you can use this to figure out what the acceleration of the crate is going to be. Okay, and I will let you handle that one.